Dear students, in this module we are going to learn about the different aspects of two variable linear regression model. We would like to see how we can have different other specifications, starting with regression through the origin. Then we would compare the R square for regression model through origin and without origin. We would then move on to the impact of change of scale and origin of measurement, in which we would divide our discussion into the changing the scale of measurement and changing the origin. So then we will move on to the impact of changing the scale of measurement and changing the origin. From there on, we will discuss about the regression on standardized variables and the functional forms, in which we would look at various functional forms, and also in the end try to understand how do we choose the best functional form, and we would then summarize about whatever we have learned in this module. So let me introduce this chapter to you, in which, as I have said earlier, we would look at various aspects of linear regression analysis. We would study the models that are linear in parameters but may be non-linear in variables. So let us start with the first specification, which is regression through the origin. Consider again the two variable population regression function where intercept is absent. Let me remind you, in our standard two variable population regression function, we have an intercept and we have a slope parameter. But now we are saying that intercept is absent. So our model now is yi is equal to beta 1 xi plus mu I. This model is named regression model through the origin. The sample counterpart of the above population regression function is the sample regression function, which is denoted as capital Yi is equal to b1 xi plus ei. We now apply OLS method to obtain the formula for calculating b1 and its variance. Since we now know that the sample regression function is yi plus bi xi plus ei, let us minimize the sum of the squares of the errors, which is sigma ei square, and is equal to sigma yi minus b1 xi square. Differentiating with respect to b1, we have derivative of sigma ei square upon derivative of b1 equal to twice into sigma yi minus bxi into minus xi. Now equating the above equation to 0, we get twice sigma yi minus bixi into minus xi equal to 0, or we get sigma xi yi minus b1 into sigma xi square is equal to 0, leading us to b1 equal to sigma xi yi upon sigma xi square. Now this is our estimate of the beta 1 coefficient in the linear regression model through the origin. Now if you substitute the population regression function in this, which is our yi is equal to beta 1 xi plus mu I, into this equation, we will have b1 equal to sigma xi into beta 1 xi plus mu I upon sigma xi square, which gives us this equal to beta 1 plus sigma xi mu I upon sigma xi square. Therefore, b1 minus beta 1 is equal to sigma xi mu I upon sigma xi square. Now taking expectation operator on both sides, we obtain expectation of b1 minus beta 1 square is equal to expectation of sigma xi mu I upon sigma xi square whole square, which means expectation on both the sides. Now since xi are non-stochastic and mu I is homoscedastic and uncorrelated, we have variance of b1 equal to expectation of bi minus beta 1 square, which is equal to sigma square upon sigma xi square. Here xi is capital Xi. Now this sigma xi is, or sigma square, is estimated by sigma hat square equal to sigma I square upon sigma xi square. So let us briefly compare the formulas in regression model with and without intercept term. Without intercept, our model is yi is equal to b1 xi plus ei. With intercept, it is equal to yi is equal to b0 plus b1 xi plus ei. The estimators b1 in without intercept model is sigma xi yi upon sigma xi square. These xi yi xi squares are capital Xi yi, whereas in with intercept model bi comes out to be equal to sigma xi minus x bar into yi minus yi bar upon sigma xi minus x bar square, which has also been written as sigma xi yi upon sigma xi square, when in this case xi yi are deviations from their arithmetic mean. Similarly, we find that variance of b1 is equal to sigma square upon sigma capital Xi square, whereas in with the intercept this comes out to be variance of b1 equal to sigma square upon sigma capital Xi minus capital Xi bar square. And similarly, we find that sigma hat square is equal to sigma ei square upon n minus 1 in the model without intercept, and in the model with intercept it is equal to sigma hat square equal to sigma I square upon n minus 2. So I am sure you can see how we can compare the different estimates obtained from the sample regression function in the models with intercept and without intercept. Now let us take an illustration to understand the application of the model which is through the origin. Now consider the capital asset pricing model, also known as CAPM, of modern portfolio theory, which states that if capital markets works efficiently, then security I's expected risk premium, which is defined as ERI minus RF, is equal to that security's beta coefficient times the expected market risk premium, which is denoted as ERM minus RF. The CAPM postulate can be empirically expressed as follows, which is RI minus RF is equal to beta I into RM minus RF plus mu I, where RI is the return on security I, RF is the risk-free return, say return of treasury bills, RM is the return on market portfolio, beta I is the measure of systematic risk, which is risk which cannot be eliminated through diversification, and mu I represents the disturbance term. Now the same relationship can be depicted through the diagram, and you can see we have on the x-axis beta I, and on the y-axis we have ERI minus RF. And you can see that the line which is the security market line passes through the origin, and the slope is nothing but ERI minus RF. And this is the illustration of the CAPM model which is given in our diagram. Now once we have understood this, let us now look at the R square for the regression model through origin. How do we define R square? Now for a regression model without intercept, the coefficient of determination can be defined as rho R square is equal to sigma xi yi upon sigma xi square upon sigma y square. I am sure students you can see that here when we have written sigma xi yi, this is not exactly the same as in a simple coefficient of determination. Their xi yi's were deviations from arithmetic mean, whereas here they are their absolute values. Similarly, in the denominator we have sigma xi square into sigma yi square. they are also capital Xi and capital Yi. The rho r square satisfies the relation which is r square is between 0 and 1, but it is not directly comparable to the conventional r square. It is good to stick to intercept model unless there is very strong a priori expectation. This is because we will be committing a specification error if there is an intercept in the model and we insist on fitting regression through the origin. Second, if intercept term is absent but is included in the model, it will turn out to be statistically insignificant. So, having understood the regression through the origin, let us now move on and try to understand the impact of change of scale and origin of measurement. So, let us first look at the changing the scale of measurement. By scale, we mean that we may divide or multiply a variable by a scalar. So, again consider our regression model, which is yi is equal to b0 plus b1 xi plus ei, which is our sample regression function in a simple regression which is with the intercept. Now, define yi star equal to w1 yi and x1 star equal to w2 xi, where w1 and w2 are scale factors and they may or they may not be equal. Now, in our regression model with yi star and xi star, we have yi star is equal to b0 star plus b1 star xi star plus ei star, which is now our equation 2, where as said earlier yi star is equal to w1 into yi and xi star is w2 into xi, and ei star is now equal to w1 ei. Now, the OLS estimates of equation 1 are given by b0 is equal to y bar minus b1 x bar. I am sure we are all familiar with this result. We are also familiar with our result of b1 equal to sigma xi minus x bar into yi minus y bar upon sigma xi minus x bar square, and with variance of b0 to be equal to sigma xi square upon n into sigma xi minus x bar square all into sigma square, and variance of b1, if I repeat, is equal to sigma square upon sigma xi minus x bar square, and we know that sigma hat square in such a model is equal to sigma ei square upon n minus 2. So, these are our standard results in a standard linear regression model. But now, if we apply OLS estimates to our new equation, equation 2, where we have used few scalars and we have redefined our variables y and xi or xi and yi, you may find that now b0 star is equal to y bar star minus b1 star into x bar star or x star bar, and similarly b1 star is equal to sigma xi star minus sigma x star bar into yi star minus y star bar upon sigma xi star minus sigma x star bar whole square. Similarly, our variance of beta 0 star is also changed, and we have now stars with all the variables, whether it is xi or sigma. Similarly, variance of b1 star also is now equal to sigma star square upon sigma xi star minus sigma x star bar whole square. And let me define sigma hat star square is equal to sigma I star square upon n minus 2. Now, if we compare the OLS estimates of both equations, what we get is that b1 star is equal to w1 upon w2 into b1, and b0 star is equal to w1 into b0. Similarly, we get sigma star hat square is equal to w1 square into sigma hat square. Variance of b0 star we obtain is W1 square into variance of B0. Similarly, we get variance of B1 star equal to W1 upon W2 square into variance of B1, and we also obtain Rxy square is equal to Rx star y star square. Now, these are our standard results. Let us look at some special cases where we may have a W1 equal to W2 or it may not be equal. So, let me start with the first case where W1 is equal to W2, which means we are using the same scalars for both x and y variables. Then I am sure you can see from the formulas that beta 1 star comes out to be equal to beta 1, and variance of B1 star comes out to be equal to variance of B1. But B0 star is equal to W1 B0, and variance of B0 star is equal to W1 square into variance of B0. So, when we have same scaling factor, the results point out that the intercept term and its standard error are multiplied by W1. However, the slope coefficients and its standard error are the same. Let us now look at some more special cases, especially suppose x scale remain unchanged, which means W2 is equal to 1, but W1 is W1, which means we have changed the scale of y but not the scale of x. In that case, you will find that B0 star comes out to be equal to W1 B0, and W1 star comes out to be equal to W1 B1, and variance of B0 star is now equal to W1 square into variance of B0, and variance of B1 star comes out to be equal to W1 square into variance of B1. The slope and intercept coefficients along with their respective standard errors are both multiplied by W1, which is the scalar we had used with the y variable. So, let us now look at the third scenario where y scale remain unchanged, which means W1 is equal to 1, but W2 is equal to W2, which means we have a scalar with x variable, but the scalar with y variable is equal to 1. In such a scenario, B0 star comes out to be equal to B0, and B1 star comes out to be equal to 1 upon W2 into B1. So, which means variance of B0 star is equal to variance of B0, and variance of B1 star is equal to 1 upon W2 whole square into variance of B1. Now, it means that the slope and its standard error are multiplied by 1 upon W2, but the intercept and its standard error are unaffected. Let us now look at the impact of changing the origin. So, after understanding the impact of change in scale, if you look at the change of origin, it means that it may affect the intercept of the regression. Now, how it does it, let us see it, and however, you will find that the slope coefficient is unaffected. The origin can be changed by either adding or subtracting a constant c to x and or y. So, suppose x star is equal to now equal to x plus c and y star is equal to y plus c. Then y star is equal to b0 star plus b1 star x star plus et. So, this is our model now. Then you will find that b1 star, which is the slope coefficient, is equal to sigma xi star minus x star bar into yi star minus y bar star upon sigma xi star minus sigma x bar star whole square. Now, which on substitution of the values of x star and y star is equal to sigma x plus c minus x bar minus c into y plus c minus y bar minus c upon sigma x plus c minus x bar minus c whole square. So, in the numerator you will find what we obtain on simplification is equal to sigma xi minus x bar into yi minus y bar upon sigma xi minus x bar whole square, which is same as b1. So, which means that when we add or subtract a basically the term in the intercept which we have defined as the change of origin, B1 star remains unaffected and is equal to B1. So subtracting a constant c from x changes the intercept in the following manner. Let us see how. Now we know that yi hat is equal to b0 plus b1 into c plus b1 into xi minus c. Now subtracting a constant c from y changes the intercept in the following manner, that yi hat minus c is equal to b0 minus c plus b1 into xi. So we see that there is an impact of change in origin, you can see, on the intercept, but not on the slope coefficient. Let us now move on and look at another specification of the regression model, which is regression on standardized variables. Now we have seen that the OLS estimates are affected by units in which dependent or explanatory variables are expressed. To avoid this problem, both the variables can be expressed in terms of standardized variables. What is a standardized variable? A standardized variable is defined to be a variable in which the mean value of the variable is subtracted from its individual values and the difference is divided by the standard deviation of that variable. Thus, standardized variables are, for example, yi star is defined to be equal to yi minus y bar upon sy. Sy is the standard deviation of yi. Similarly, xi star is equal to xi minus x bar upon sx. So y bar is equal to sample mean of yi, sy is equal to sample standard deviation of yi, x bar is equal to sample mean of xi, sx is equal to sample standard deviation of xi. The mean value of a standardized variable is always 0 and its standard deviation is always equal to 1. That is why they are known as standardized variables. So we could run a regression on the standardized variables as yi star is equal to b0 star plus b1 star xi plus ei, which is equal to b1 star xi star plus ei star, because intercept term now is 0 in the standardized regression, because intercept we know is equal to y bar minus b1 x bar, and in this case you will find that yi star bar is 0 and similarly xi star bar is also equal to 0. So what is the interpretation of this regression coefficient b1 star in our new regression equation? This basically means that if the standardized explanatory variable increases by 1 standard deviation, on an average the standardized dependent variable increases by b1 star into standard deviation units. The standardized regression model has advantages over the traditional regression model. Now, when all the regressions are standardized, we give them equal basis and are able to compare them directly. The size of the coefficient of a regressor in this case indicates its contribution to the regressant. A regressor with large coefficient contributes more to the regressant than a regressor with a smaller coefficient. Therefore, the regressor coefficient measures the relative strength of the various regressors in this situation. Now, there are two things to be noted in this. First, the notion of R square is not applicable to standardized regression, as it is regression through origin, which we have discussed earlier also. Second, there is a relationship between regression coefficient of standardized model and traditional model. The relationship for bivariate case is as follows, that b1 star is equal to b1 into sx upon sy, where, as we said earlier, sx represents the standard deviation of the x regressor, and Sy represents the standard deviation of the y regressant. Let us now look at some more functional forms in this section. Now, for many of the economic applications, you will find that the relationship between variables is non-linear in nature. So, let us extend our linear regression model to incorporate non-linearity in variables by appropriately redefining the dependent and the independent variables. In the beginning, let us consider the following regression model. So, let us presume that yi is equal to beta 0 plus beta 1 ln x plus mu I, where x is again the exogenous variable and ln x is the regressor. Now, take another regression model where we may have ln yi is equal to beta 0 plus beta 1 xi plus mu I, where now yi is the endogenous variable and ln yi is the regressant. Now, both the above models are linear in the parameters, although they are not linear in the variable x in the first case and variable y in the second model. Now, since both the models are linear in parameters, OLS method can still be used to estimate the parameters. However, if the model are not linear in the parameters, iterative methods must be used in the estimation. Now, there are certain nonlinear models which can be made linear by suitable transformation. For instance, the standard Cobb-Douglas production function with disturbance term in a multiplicative form is equal to y equal to e raised to power beta 0 plus x raised to power beta 1 into e raised to power mu. This is the multiplicative form of the Cobb-Douglas production function. Now, if you take the natural log on both the sides, we will have ln y is equal to beta 0 plus beta 1 ln x plus mu I. Now, so it has become a linear model by logarithmic transformation. However, if in this model, if the disturbance term is an additive form, we will have y equal to e raised to power b0 into x raised to power b1 plus mu I. Now, this is a non-linear model and we cannot transform this model into a linear model by taking log of both the sides. Before we proceed to various functional forms, we will look at few definitions which will help us later. The first is the proportional change between x2 and x1 is given by delta x2 upon x1 and is equal to x2 minus x1 upon x1. To obtain proportional change in percentage, we multiply this proportional change by 100. So, 100 into delta x2 upon x1 into percentage is almost a percentage change. So, the logarithmic change between x2 and x1 is given by delta ln x, which I am sure all of you would know is equal to ln x2 minus ln x1. In terms of percentage, the logarithmic change is 100 into delta ln x percentage. Let us in a table try to have an examples of proportional change and logarithmic change. So, let us presume x2 is equal to 102, 110, 140, 160, 200 and x1 takes the values 100, 100, 100, 100, 100. So, proportional change in percentage is equal to 2%, 10%, 40%, 60% and 100%. Whereas, if you measure the logarithmic change in percentage, you will find that this log change in percentage is equal to only 1.9%, 9.5%, 33.6%, 47% and 69.3%. When the change is small, proportional change and log change are almost equal. But as the change gets larger, the difference between them widens. Now here, let me introduce the concept of elasticity. Elasticity measures the ratio of relative change of two variables. In terms of proportional changes, the elasticity of y with respect to x can be defined as elasticity of y given x is equal to delta y upon y1 upon delta x upon x1, where delta y is equal to y2 minus y1 and delta x is equal to x2 minus x1. Now, in terms of log change or logarithmic change, the elasticity of y with respect to x can be defined as elasticity y given x equal to dy upon y upon dx upon x, which is equal to derivative of log y upon derivative of log x. Here derivatives are natural derivatives, so natural logs we are using. The logarithmic definition of elasticity is usually used in econometric models. So let us now consider various functional forms which are linear in parameters. We will also interpret the meaning of marginal effect of xi on yi in each such case. Marginal effect is nothing but change in yi as a result of change in xi. Let us look at the various functional forms of the regression model. Some of the functional forms which we are going to use are the log-log model, the semi-log model, the reciprocal models, and the logarithmic reciprocal model. First, let us look at therefore the log-log model. In the log-log model, let me repeat again, our model is used mainly in our production function or demand functions, and we can have an exponential regression model which is expressed as yi is equal to b0 into xi raised to power b1 into e raised to power ei. Now this can be written alternatively as ln yi is equal to ln b0 plus b1 into ln xi plus ei, where, as I mentioned earlier, ln is natural log, which means it is log to the base e, and e is equal to 2.718. We rewrite the above equation as follows, which is ln yi is equal to a plus b1 ln xi plus ei, where a is equal to ln b0, and such models are known as log-log or double log model. The log-log model can be estimated by ordinary least square method because it is a linear model in parameters, and we can rewrite this model as yi star is equal to a plus b1 xi star plus ei, where we may define yi star is equal to ln yi and xi star is equal to ln xi. The OLS estimators a and b1 are unbiased estimator because of the OLS. The popularity of the log model lies in the slope coefficient b1, which measures the elasticity of y with respect to x. For instance, if y represents the quantity demanded of a commodity and x represents its price, then b1 measures the price elasticity of demand, which is a very popular concept in economics. I am sure those who have the background of economics would appreciate it. Therefore, the log-log model has, you will find, many features, and now two special features are enumerated here. First, the elasticity coefficient between y and x remains constant throughout the model. So no matter at which point of ln xi you measure the elasticity, it will remain same. Second is, even the estimator b0, which is nothing but the anti-log of a, is a bias estimator, although a is an unbiased estimator. However, the intercept terms are not very important in empirical studies. Let us take an illustrative example. Consider the following results of the estimated regression model between consumption expenditure and income. So let's presume that ln xpi is equal to minus 4.0563 plus 1.5 4871 ln Inc. I, where EXPI is the expenditure of the ith individual and INCI is the income of the ith individual. Now this result is based on the data collected from different individuals. Here we find that the elasticity of consumption expenditure with respect to income is about 1.5. Exactly it is 1.4871, indicating that if income increases by 1%, then the expenditure increases by 1.5%. So let us look at the linear log model. The lin log model helps us to find the absolute change in dependent variable yi for a percentage change in independent variable xi. A linear log model is given by yi is equal to b0 plus b1 into ln xi plus mu I. The slope coefficient of a lin log model is defined as follows. It is defined as b1 is equal to change in yi upon change in ln xi, which is same as change in yi upon relative change in xi. Symbolically, the slope coefficient can be represented as follows, that b1 is equal to delta yi upon delta xi upon xi, where delta denotes a small change. Alternatively, the above equation can be written as delta yi is equal to b1 into delta xi upon xi. This above equation states that the absolute change in yi, which is delta yi, is equal to slope times the relative change in xi. So if we multiply the latter by 100, then the above equation gives the absolute change in yi for a percentage change in xi. The most practical application of the lin log model can be found in the Engel expenditure models. According to Engel, the famous economist, the total expenditure spent on food increases in arithmetic proportion and total expenditure increases in geometric progression. Having understood this, let us now try to understand another form, which is log linear model. In log linear model, we are often interested in calculating the growth rate of important economic variables such as GDP, money supply, population, employment, etc. So suppose we are interested in finding the growth rate of a variable y using compound interest formula, which is yt is equal to y0 into 1 plus r raised to power t, where r is the compound growth rate of yt. Now taking log on both the sides, we will get ln yt is equal to ln y0 plus t into ln 1 plus r. Now suppose we denote b0 is equal to ln y0 and b1 equal to ln 1 plus r, the above equation can be rewritten as ln yt equal to b0 plus b1t. Now this t, if you add error term to the above equation, can be rewritten as ln yt equal to b0 plus b1t plus et. And this above model is known as the semi-log model, because you can see that only one variable is in log form, and here the explanatory variable is linear and the dependent variable is in log form. So it is called lin log model. In lin log model, the slope coefficient measures the relative change in dependent variable for a given absolute change in the value of the independent variable. Hence, b1 can be defined to be equal to relative change in dependent variable y upon absolute change in independent variable x. Now, growth rate of yt can be obtained by multiplying b1 by 100. So, multiplying b1 by 100 is also known as semi-elasticity of y with respect to x. The b1 coefficient gives us the instantaneous growth rate of the dependent variable y. However, this is not the compound growth rate over a period of time. The compound rate of growth could be found by taking the anti-log of estimated B1 and subtracting 1 from it and multiplying the difference by 100. Let me remind you that the compound growth rate is given by R. So, this R can be calculated only by taking the anti-log of the estimated B1 and subtracting 1 from it. That you can verify from the formula which we have demonstrated above. Let's now move on and look at another model which is known as linear trend model. A linear trend model can be written as follows, which is yt is equal to b0 plus b1t plus et. Here we regress y on time, unlike in log-laden model where we regress L and y on time. Now, the time variable t is known as the trend variable. We have downward trend in y when the slope coefficient is negative and upward trend in y when the slope coefficient is positive. The choice between the growth rate model and the linear trend model will depend on whether we are interested in the relative or absolute change in the variable of our interest, which is y. Let's take an illustrative example. Consider the regression result for growth rate of expenditure on private consumption over a period 1990 to 2010. In that case, the estimated equation is ln exp is equal to 6.3412 plus 0.00743 t. Now, find the instantaneous growth rate of expenditure on private consumption over a period 1990 to 2010. This is an exercise which you can do. Also, we can find the compound growth rate on expenditure over the period 1990 to 2010. Let's look at the solutions. The solution of the instantaneous growth rate is 0.743%, which is nothing but the coefficient of t multiplied by 100. Whereas the compound growth rate is anti-log of 0.00743 minus 1, and it comes out to be equal to 0.00746 or 0.746%. So we can see that the instantaneous growth rate is 0.743% and the compound growth rate is 0.746%. Let's look at another model which is used in economic theory, and this model is known as reciprocal model. A reciprocal model is given by yt is equal to b0 plus b1 into 1 upon xt plus mu t. The above model is non-linear in the variable xt as it enters reciprocally, but it is linear in parameter b0 and b1. As the independent variable xt increases indefinitely, the term b1 into 1 upon xt tends to be equal to 0, and the dependent variable yt approaches its limiting value b0. Now, let us take an illustrative example. Consider the modern version of Phillips curve, which can be expressed as pi t minus pi t raised to power e equal to beta 2 into unt minus u raised to power n plus et, where pi t is defined to be actual rate of inflation at time period t and pi t e is equal to expected rate of inflation at time period t based on period t minus 1. Now, it is usually replaced by pi t minus 1 since expectation inflation is unobserved. Now, unt is defined as actual rate of unemployment at time period t and u raised to power n is defined as natural rate of employment at time period t. Et, as usual, is our error term. In empirical studies, the relationship between inflation and unemployment can either take a linear regression model and or a reciprocal model. If you define it by a linear model, then we may have pi t minus 1 equal to 3.4671 minus 0.5789 UNT. And in a reciprocal model, the estimated equation may come out to be pi t minus 1 equal to minus 2.4128 plus 13.6412 into 1 upon UNT. The linear model shows that if the unemployment rate goes down by 1%, then on an average the rate of inflation will go up by 0.5789 percentage point and vice versa. On the other hand, the reciprocal model shows that even if the rate of unemployment increases indefinitely, the rate of inflation will come down to at most 2.4 percentage point. Therefore, the natural rate of unemployment can be calculated from the linear model as given below. Now, this natural rate of unemployment is equal to, therefore, u raised to the power n or un equal to b0 upon minus b1 and is equal to 3.4671 upon 0.5789 and is equal to 5.989. Thus, we can say that the natural rate of unemployment is about 5.989% approximately. Let us look at the last model, which is also a reciprocal model, but we are defining it as a log reciprocal model, in which the logarithmic reciprocal model take the form ln yi is equal to b0 plus b1 into 1 upon x plus mu I. Now, such model can be used to capture the production function in short run. Our knowledge from microeconomics tells us that if labor and capital are the inputs in production function and we keep capital constant and keep increasing the labor input, then the short run output labor relationship will be captured by the log reciprocal model. Having understood these different models, the question which arises now is that how do you choose the best functional form? And therefore, we have to make a choice between these different functional forms. Now, the choice of the most appropriate functional form for empirical analysis requires lots of skill and knowledge of economic theory and other information. The choice becomes more difficult as the number of explanatory variables increases in the model. However, some practical guidelines for choosing the best appropriate forms are: first, the economic theory may help us in selecting a particular functional form, for example, the modified Phillips curve. The second criterion could be, or second in a way you can see guideline could be, that it is useful to calculate the slope coefficient of the regression model and the elasticity of the dependent variable with respect to the explanatory variable. Now, the following table may be of help in this. In this table, we have taken different models and we have taken the equation, and we have also defined the slope, which is dy upon dx, and the elasticity, which is equal to dy into x upon dx into y. And you can see how we can find out the slopes and elasticities for these different models. The third guideline is that the regression coefficient of the chosen model should be in conformity with the priori expectation according to economic theory. For instance, if we consider the demand function of a commodity with respect to its price, then the slope coefficient should be negative, because we know that there is an inverse relationship between price of a commodity and its quantity demanded. It is also possible that more than one functional form satisfy the data very well. For instance, we can fit both linear and reciprocal model to the modern version of Phillips curve. Therefore, the usefulness of the coefficient of determination we may use, but it should not be overemphasized. As we add more explanatory variables to the model, we will have higher values of R square. What actually is important is the correct sign of the regression coefficient, which should conform economic theory and their statistical significance. So let us now try to summarize what we have learned over this entire module. Now, the first thing we have learned is that if a regression model does not contain an explicit intercept term, it is known as regression through the origin, and one should be cautious with estimating such models. In such models, the sum of the residual sigma ei is non-zero, and conventionally R square may not be meaningful. It is better therefore to introduce the intercept in the model explicitly unless there is a strong theoretical reason to exclude the intercept. The second thing which we have learned is that the interpretation of the regression coefficients depend on the units and the scale in which the dependent and the independent variables are expressed. We have also discussed some important functional forms in this module, where some of these are in fact the log linear or constant elasticity model, the semi-log regression models, and the reciprocal models. We have also understood, I am sure, that in the log linear model, both the regressant and the regressor or regressors are in the log form. The regression coefficient attached to the log of an independent variable is interpreted as the elasticity of the dependent variable with respect to the independent variable. So in a double log model, we can directly find out the elasticities. In the semi-log model, where the dependent variable is logarithmic and the independent variable is time, the estimated slope coefficient multiplied by 100 measures the instantaneous rate of growth of the dependent variable. In the semi-log model, if the independent variable is logarithmic, its coefficient measures the absolute rate of change in the dependent variable for a given percentage change in the value of the independent variable. In the reciprocal model, either the dependent variable or the independent variable is expressed in reciprocal or inverse form to capture non-linear relationships between economic variables. We have also understood and discussed that the choice of most appropriate functional form requires experience and knowledge of economic theory. Instead of giving importance to the value of R square, we should look at the sign of the regression coefficients. Thank you very much, students.